Let us now consider this next question on the board. Okay, if A is equal to 6i minus j plus 3k, for what value of P is the vector B equal to 4i plus pj perpendicular to vector A? For what value of P is the vector B perpendicular to vector A? How do we approach this question? I want to pick the word that this vector B is perpendicular to vector A. Now, when you go back to properties of scalar, we learn that when two vectors are perpendicular, their scalar product is equal to what? 0. Because when they are perpendicular, it means they are orthogonal. The angle between them is 90 degrees. And when you do A dot B, which will give you magnitude of A times magnitude of B cos 90, that cos 90 is equal to 0. Which simply means that A dot B will be equal to 0 in that case. And that is the principle we use in solving this problem. So I have vector A here to be equal to 6i minus j plus 3k. Then we'll have vector B to be equal to 4i plus pj. So what do we do here? Remember, like we stated, for A and B to be perpendicular, so I'm going to write for B to be perpendicular to vector A. So to A, comma, it means that A dot B, that is the scalar product of vector A and vector B will be equal to 0. That is the principle. That is the secret of handling a problem like this. So how do we go now? Let's do A dot B and C. So A dot B will give us 6i minus j plus 3k. So dot B and B is 4i plus pj. There is no k component here, alright? So that's equal to 0 there. That's the k term is equal to 0. That is the z component. Is that okay? Z component, then unit vector k. It doesn't appear here, so it simply means it's 0. If I like, I'll put it. If I don't like, I'll leave it. But let me just put it for the sake of clarity and emphasis. So what do we do? Let's now find the dot product. We go 6i dot 4i will give us 24. And then minus j dot pj will give us minus p. And then 3k dot 0k will give us 0. And then everything would be equal to what? 0. Take note please, 3 times 0 is 0. So that z component goes off. You can see clearly that the value of p is equal to what? 24. So what it simply means is, if p here is 24, then A and B are orthogonal, are perpendicular. You can actually prove that. Is that okay? You can actually prove that. And how would you prove that? I would give you a self-test work. Self-test. Remember, these are answers. Okay, self-test. Show that vector A and B are orthogonal. Alright, now how do you do that? I'll give you a hint. Find out that theta, the angle between A and B, equals 90 degrees. That is how you prove this. And of course, to go about that is simply, remember the dot product formula, which is A dot B equal to magnitude of A times magnitude of B cos theta. You know how to calculate the angle between two vectors using scalar product. So use that, and by the time you get theta to be equal to 90 degrees, it simply shows that truly vector A and B are what? Perpendicular or orthogonal. But remember, to do that, you've already gotten P to be 24. It's only when P is 24 that these two vectors will be orthogonal based on what we solved. So substitute 24 here and then find the angle between A and B. If you get 90 degrees, it means that truly they are orthogonal when P is equal to 24. In our next video, we're going to look at problems on cross product, vector product of vectors. We now have this fourth question here on the board, still on application of scalars and vectors. So let us look at the question. We're asked to calculate the moment of the force F about O from a position vector R if F is equal to 3i plus 4j plus 5k in Newton and R is equal to 6i plus 5j plus 3k in meters. So So we have to determine the what? The moment. So what we need to do first is to ask ourselves, moment, is it a scalar quantity or a vector quantity? Because the parameters given to us here to use in determining moment, they are vectors. Force and this R here, they're given in vector form. So we have to ask ourselves, to get to our moment then, is moment a scalar quantity or a vector quantity? You would recall that we classified moment as a vector quantity. Therefore, to obtain the value of that moment, since it is a vector quantity, we are going to do the vector product or the cross product of the force and the position vector given to us there. So let's do this and see moment. Permit me please to use capital letter M for moment. By definition, it is F cross R. F cross R. Is that okay? F cross R. Now, if this is our moment, remember the definition of cross product in terms of its component. If you're given component of vectors, the ijk component, you're going to extract a 3 by 3 square matrix from the given vectors, starting with your ijk, then the second row, of course, the element of the first vector, the third row, the element of the second vector. So let us do that and see. Our moment is not equal to, we're going to extract ijk from these vectors given to us. Then, since moment is force cross the position, we're going to impute the scalar component of the first vector in the second row, which happens to be 3, 4, and 5. So I have 3, 4, and 5. Then in the third row, the scalar component of the position vector, which is 6, 5, and what? 3. And how do we proceed to solve this? Remember, the first thing we need to do is to introduce our plus, minus, and what? Plus. Then going by solving this, the moment, which we again produce a vector for us, because we know that the vector product, the cross product of two vectors will produce a vector. Now we start by keeping plus I constant. So I is constant, this I. The column will disappear, the row will disappear, it will go off. Now I'm going to ask you a question. If you pick this I and its column goes off, its row goes off, what matrix will be left? You'll be left with a 2 by 2 square matrix, which is this 4, 5, and 5 what? 3. So how do you do the multiplication? You go this way first, alright? This is first, and then you come this way second. You come this way second. And of course, between the result you're going to get in the first movement and the result you're going to get in the second movement, you put minus between them. Alright? So in our previous video, we already established that under vector product. So we go. This is going to be 4 times 3, which will give us 12, minus 5 times 5, which will give us 25. So you notice, first move, second move, minus between them. The next, you pick minus j. The column of minus j will disappear, the row of minus j will disappear. Once that happens, you'll be left with 3, 6, 5, and 3. So you go 3 times 3, which will give us 9, minus 6 times 5, or 5 times 6, which will give us what? 30. Then lastly, we pick plus k. So I have plus k, do same. The column of k will go off, the row of k will go up. So you notice that the first row always goes up. And then once that happens, you'll be left with 3, 4, 6, 5. So you move 3 times 5 will give us 15. Then minus 4 times 6, which will give us 24. So this is your first multiplying move in solving this matrix that you obtain there. So that our moment will now be equal to 12 minus 25 is going to give us minus 13. Minus 13 from here times I will give us minus 13i. Minus 13i. Alright, minus 13i. So we move on to the next one, the j aspect. We have 9 minus 30. 9 minus 30 will give us minus 21. Is that not so? Minus 21. Then you have minus outside there. Minus times that minus 21 will give us plus 21j. And then the last time there is 15 minus 24. 15 minus 24 is going to give us minus 9, right? Then that minus 9 times plus k will give us minus 9k. So this is the moment of the force. This is the moment of the force about this point O. Is that okay? Now this could be our result. But just imagine that you're seated in an objective case and the examiner chooses not to leave the options in vector form. Possibly it's the magnitude of the moment that the options are presented, which means we can also proceed to obtain the magnitude of this. I'm going to write or. We can do the magnitude of the moment. The magnitude of the moment is going to be obtained as square root of 13. Remember, I've told you when I'm dealing with this, I don't bother myself with the signs. So plus 21 is going to be squared, then plus 9 we square it. So let us see what the magnitude of the moment is going to give to us. And of course, you know the magnitude of the moment is still the same as the magnitude of F cross R. Because moment by definition here is F cross R, we have that. So what's going to be the magnitude? This time around, let's reach out for a calculator. We have square root of 13 squared, 21 squared, and 9 squared. So square root, open brackets, 13 squared, then plus 21 squared, plus 9 squared. Close bracket. So from here it's giving me 26.28. Let me make it 26.3. So that this is the moment in terms of its magnitude. And what's the unit? Newton meter. This one is Newton meter. So the result can be left in form of this vector like this, or the result can be given in terms of the magnitude of the moment. Either case is still correct. If it is in theoretical case, you have to solve up to these points so that you have alternative results or answers which are also the same. But in objective case, your examiner may choose to leave your answer in vector form, knowing that the vector product, the cross product of two vectors will give you a vector. Or the examiner might choose to give you the option in terms of the magnitude of the cross product, which in this case happens to be this. Now we have this question on the board that's about torque experienced by a particle. Is that okay? So let us look at this question together. If at a position of r equal to I plus 2j plus 3k, a particle is acted upon by a force F equal to 4I plus 5j plus 6k, the torque experienced by the particle is, we don't know. Okay, so we didn't know the value of the torque that the particle is going to experience. We are required to obtain the value of the torque. Now, the first thing here is to know what torque really is about. So first, I'd like you to know that torque is the rotational dynamic analogy to work. Why we deal with work when talking about linear motion and the rest of them, is that okay? When you're talking about rotational motion, we talk about torque. So torque serves the same function as work. Just like, for example, you talk about velocity in linear motion, you use v. In circular motion or rotational motion, that velocity, you use angular velocity, which is omega, okay? So that's how torque and work goes. Now, just think about a knot screwed to an object, and you want to lose the knot. What do? Usually? You bring a spanner, you fix up the spanner to the knot, and then you turn. Is that not so? There is a mechanical advantage that is produced, which leads to the turning and the loosening of the knot. That mechanical advantage depends on, one, the force that you apply to the knot trying to lose it, and two, the wrench handle, the handle of the spanner that you are using. Are you following? And that handle of the spanner you are using to where you held the spanner to turn, there is a distance. That distance is this radial vector called this position here. Is that okay? This radial vector R. Now, once you apply that force, you turn. There will be this circular motion. The physical quantity that produces this effect, that caused this turning, is what we refer to as torque. According to the study of scalar and vector, torque, T-O-R-Q-U-E, which I'm going to use these Latin alphabets. That alphabet, Greek alphabet, is called tau. So that's what we use for torque. Is equal to the cross product of the radial vector and the force. That's the position there, and the force. So that's the definition. Is that okay? And because torque is a vector quantity, that's why we're using cross products to obtain it. Okay, now let us do this together. We know by definition the cross product of these two vectors is going to be the 3 by 3 square matrix obtained from this. We'll have our ijk fixed. Then you introduce the scalar component of r first. Here the component is 1. So you fix in 1, you have 2, you have 3. Then you now go to the third row, the scalar component of the force, which is 4, 5, and what? 6. You know how we used to do this? We solved previous question on cross products. So we're going to apply the same principle. Come over here and put plus minus what? Plus. And then we are set to solve. Our torque is now going to be, we pick out our I, then the column of I will go off, the row of I will go off. You'll be left with this 2 by 2 square matrix. You do 2 times 6, which is going to give us 12, minus 3 times 5, which is going to give us 15. The next, you pick minus j. the column of minus j goes off, the row of minus j goes off, you'll be left with 1, 3, 4, 6. 1 times 6 is going to give us 6 minus 3 times 4, which is 12. And lastly, we have plus k. The column of k goes off, the row of k goes off. You know the matrix or the elements that will be left: 1, 2, 4, 5. 1 times 5 is going to give us 5 minus 2 times 4, which is going to give us 8. Now let us simplify that and see what the torque is going to be like. So 12 minus 15 will give us minus 3. Minus 3 times this plus I will give us minus 3i. Next here you get minus 6 from these brackets times minus j outside, that will give us plus 6j. And then lastly 5 minus 8, which will give us minus 3. Minus 3 times minus k times plus k rather will give us minus 3k. So this is the result of the torque. The unit of the radial vector and the force was not given to us, so we can just put unit here. Is that okay? But you know, generally force is given in Newton and then this position in meter, which means that torque has the unit Newton meter. But since the units of these quantities were not given, let's just leave it as unit there. Remember, there's something I told you in previous question number 4. An examiner may choose to solve this thing and give you options in terms of the magnitude of the torque. So if I proceed to obtain the magnitude of the torque, which is also equal to magnitude of R cross F, you know, and of course, you know the definition of cross product. This is going to be magnitude of R times magnitude of F, then times sine of the angle between them. Okay, fine. So on the basis of this, the magnitude of the torque, you know, in terms of the components, because the torque now we know the component, we can actually use Pythagoras theorem for it. Still remember, I didn't pick this minus. I've told you the reason before. The negative sign is irrelevant when you're calculating magnitude of something. Magnitude is always positive. So this is going to give us this value there, so that the magnitude of the torque, this is 9, this is 9, 18, this is 36. 18 plus 36 should give us 54. So this is square root of 54. We can leave our result like this if we want. If you don't want to leave our result like this, we can also present it as 9 times 6 will give you 54. And then square root of 9 is 3. So we can have it as 3 root 6. Is that okay? If you don't want to leave it like this, you can actually find the square root of 54 directly, which if you do that, you get 7.3 approximately. So any of this can be the result. Is that okay? So I'm going to put units. Suppose we know the unit of the force given and positioning that were given in the question, then we'll put the unit of the torque, which of course is Newton meter. Quickly before I leave the stage, I want to point out something to you. Did you take note that moment and torque are quite related? They're somehow related. Now what's the difference? It's in terms of how you place the cross product. For moment, it is force cross R. So you have F cross R. Is that okay? But for torque, it is R cross F. Take note. Of course, you know that vector multiplication, that is cross product, is not commutative, which means the order of arrangement matters. Please don't mix up these two concepts.